Hey guys, so there's a Div 3 today, and well, just look at this. This went really, really well. Yeah, I won this round, which is really cool. And there's a bit of a technicality, but let's just forget about that. So, yeah, this was cool. Finished in 23 minutes and then was first to finish, which is nice. And yeah, so I have nothing more to do but go over solutions. So let's do that. Hopefully this should be quick. And then we can have these out relatively soon. But yeah, I don't have much to say other than just wow. Yeah, winning a round. Hopefully you don't get hacked, because that's always a possibility for everyone, but ideally that wouldn't happen. We'll see. Okay, close that. Now let's do some problems. So we have this problem A, and essentially what we're going to do is we're going to insert some elements in between elements of this array. And what we want to do is we want to make it so the like, consider any two adjacent elements. Let like A be the smaller one and B be the larger one. Then we want the difference, or we want B divided by A to be less than or equal to 2. And all we can do is insert elements in between. So say we do insert some element. Let it be x. Then if x over 2 is greater than 2 and 10 over x is greater than 2, then like inserting x is just sort of not that helpful, because it forces us to do even more moves in the future. So what we want to do is we want to make x within 2 of at least one of these. We would either want 10 over x to be less than or equal to 2, or x over 2 to be less than or equal to 2. Either way, we want one of those to be true. And if we have this being true, then the best thing we can do is make x as large as possible, and that way what we can do is we can make it so we have the smallest amount of moves to make it so it's also within 2 of 10. And the best way to do that is to make it as large as possible, assuming 2 is the smaller element. So what we can really do is we can put x equals 4, which is 2 times 2. And then if that still doesn't work, then we need to insert another element here, and now we have the same situation. We want to insert 2 times 4. So we would do 4 and then 8, and then we would do this until we satisfy the constraint. So we can do this for each adjacent gap of elements, where we just find the smaller and larger element and then keep inserting 2 times the previous element until we're done. So for example, if we have 1 and 100, we would insert 2 times 1, which is 2, and then 2 times 2, 4, and then 8, and then 16, and then 32, and then 64. Yeah, 64. And then at this point, 64 and 100 are within 2, so we're good. Basically, this checks the same thing. It's basically while 2 times the previous element is less than this one, which is equivalent. You can play with the equation if you want to check that. And so this is, because we multiply by 2, it's O of log of AI per gap of adjacent elements. So there are O of n 50 gaps of adjacent elements, and the elements are up to 50, so this is like less than n squared, which is totally fine. So that's how you would do A. For B, you have a number and an array. Or you have an array of size n. And basically what you want to do is, in one move, you can increment an element. So you can make it +1 and make it equal to 6 or something. And what we want to do is consider all the numbers modulo 3. That is, consider the remainder of their division with 3. So 0 modulo 3 would be 0, 2 modulo 3 would be 2, 5 mod 3 would be 2, 5 mod 3 is 2, 4 mod 3 is 1, 8 mod 3 is 2. And what we want to do is we want to increase these numbers so that the number of numbers that have remainder 0, the number with remainder 1, and the number with remainder 2 are all the same. It's also guaranteed that n is divisible by 3, so this is possible. So in this case, the number we need to achieve is n over 3, which is 6 over 3, which is 2. So we need to have 2 zeros, 2 2s, and 2 1s. Currently we have 4 2s. So all we can do is increase. So let's assume we want to make 4 2s. Then the only way we can get rid of these 4 2s is by increasing some of them. And we want to make it so we have exactly 2, so let's get rid of 2 of them. Now these 2's get converted to zeros. For example, this would be added to a 6, and this would be added to a 9, which is not intentional, but yeah. So now both of these have remainder 0. But now we have 3 zeros, and we need to make it so we have 2 zeros, so we can then get rid of the zeros. And then, or we can get rid of 1 0 and have that become a 1. And then we would have 3 2s, 3 zeros, and 3 1s. And the way to do this is to simply iterate in order. So first we look at 0. Do we have too many zeros? If so, convert some of them to 1 so that we have exactly n over 3 of them. And then we iterate through 1. Do we have too many 1s? If so, convert some to 2. And do we have too many 2s? And if so, convert some to 0. And then now the problem is after this, we might still have too many zeros because making this move might now make us have too many zeros. So once again, I think it's enough to only check 0, but it can't hurt to just check everything again one more time. And through the second iteration, we won't have too many anymore because we'll have guaranteed looked at each element at least twice. And we'll have done all the shifts that are necessary. So really we just look at 0, move some to 1, enough to make it exactly n over 3. Then we look at 1, look at 2, look at 0, look at 1, look at 2 again. And then each time we move elements up if there are too few of them. So yeah, that's the idea. So basically this is what we do. We do this twice. 2 times we look at each element from 0 to 3. And if it has too many, we move some of them over and increment the answer because each one takes an operation. For C, we have a number x, and we want to see, we have a number x where x is up to 10 to the 12th, and we want to see if there exists 2 numbers a and b where x is the sum of their cubes. So we want to find a and b where a cubed plus b cubed is equal to x, and a and b must be positive, so strictly greater than 0. So 10 to the 12th is important. It means we can't just iterate over a. But actually it turns out we can. Because consider when a cubed is greater than x. Then no matter what, because b cubed has to be positive, like there's nothing we can do to counteract this. We're sort of just screwed. In that there's nothing we can do. There's no possible b when a cubed is already bigger than x. So therefore we only have to consider a where a cubed is less than or equal to x. And how many possible a are there here? Well, this constraint is equivalent to a being less than or equal to the cube root of x. And the cube root of 10 to the 12th is 10 to the 4th. So really we only have to iterate a up to 10 to the 4th. So with a fixed a, now we want to find some b such that b cubed is equal to x minus a cubed. Note that this whole thing is constant now because we fixed a. So really we want b to be the cube root of this equation. And we can literally just take this cube root with our programming language and just see if b is an integer or not. Alternatively, we can find the b, and then to check if it's an integer and if it works, just check if b times b times b is equal to this quantity. And in fact, that's what I do. So I'm going to iterate over a, which I call it, and then compute this value, x minus a cubed. And then I take the cube root using the C++ function cube root L, And that basically just does cube root for long, so it's better precision. And then I'm doing some manual correction here because I don't trust precision errors. So like it could be off by 1 or 2. So I'm simply just manually correcting it so that if it's less than, I'll make it higher than or equal to, and if it's greater than, I'll make it less than or equal to. And that way it'll be corrected if it's a perfect cube, then it will be corrected no matter what, and if not, then it won't matter anyway. So I'm just making sure I'm being careful with precision. And then after that, we just simply check things. Yeah, we just simply check if it's possible. So that'll be how that works. For D now. We have a permutation, and we're going to build a tree out of this permutation. So let me show you how this works. 1, 3, 2, 7, 5, 6, 4. So what we're going to do is we're going to pick the maximum element, and then we're going to create a node for this element. And then now, from this node, we create 0, 1, or 2 possible branches, where these branches represent the rest of the arrays. So we're going to sort of pick the maximum element, and it's a permutation, so it's guaranteed there's a unique maximum. And then we split the array at this maximum. So now we have 2 different sides of this tree, and they represent this and this. So let's create these 2 nodes. And we're going to once again find the maximum. So, actually, wait, let me do that. So this represents the green split. And then the orange nodes are going to be the new maximum. So this is the maximum of this array, and this is the maximum of this array. So we create 2 nodes for that. So this is going to be node 7, this is going to be node 3, and this is going to be node 6. And then now we once again split these arrays. So say we do purple splits, we have 1 and 2 and 5 and 4. So we would create these edges. And then you get the point. We find the maximum again, we create all these nodes, etc. And this will represent 1, 2, 5, and 4. And now what we want to do is, given that we're going to construct the tree this way, we want to figure out for each position, not for each value, for each position, what depth it's going to have in the tree. And that means like how deep is it? How far is it from this starting node? So really this is just sort of implementation. We basically define a function where we do recursion, where we do solve of left and right. And then within this, what we do is find maximum. So we find the position of the maximum, call it P. And we can do this by just iterating through this whole range. Then create the node P. And in fact, it may be convenient to also include the depth in this solve, like the current depth, and that way we don't have to actually construct the tree, kind of. We just imagine we're creating a node at position P. Then the answer at this position is going to be the current depth we're at, because that's going to be the node we create. And then now we split, like say we have L, R, and then P. So now we split this up into 2 ranges, as the problem says, from everything excluding P on the left and everything on the right. And then we simply call solve L and P minus 1, and solve for P plus 1 and R, representing the left and right sides respectively. And we return whenever when L is greater than R, because that means we have an invalid range. Like, it just means we're done. So really, it's just sort of implementation. We're going to find the maximum, set the answer to that current depth. Oh, and actually this should be and then depth plus 1. We increment the depth both times because now we're going deeper. So then this would be solve for P minus 1 plus 1, R, and then also depth plus 1. sort of mess it up. But yeah, like in the code, we're just doing that. We do this if L is greater than R, return. Otherwise, find the index of the maximum, and then set the depth to that, and recurse. And that's it. And the reason this works is because simply when we split the array, we have a completely independent subproblem, and we're just solving on that range. So we can sort of do this sort of recursion because we're splitting up ranges. In total, this will take at worst O of n squared because we find the maximum each time and we have O of n layers. You can speed it up with something like a segment tree, but it's a div 3. It's not necessary. Okay, so at this point I'm going to stop going over code because it's less necessary. So now we have E, and we're going to yeah, so now we have E, and we're going to figure out how this works. So we have a bunch of players. Each one has a certain number of coins. And then we're going to play a tournament. And we can choose the way this tournament is played. So we can, in short, pick 2 players and have them play a game against each other. Now, they say random, but what that really means is that we can do whatever we want. We can have it go however we want and sort of optimize it for our current player. So we're trying to figure out, for each player, can it possibly win the tournament? And actually, how many players could possibly win the tournament? And you can win if you win all the games you're in, and you win a game if the current number of coins you have is greater than or equal to the current number of coins your opponent has. Note that again, equal because the choice is random, but that means that we can do it in our favor because we just want to have any possible chance of winning. So of all possible outcomes, is there one in which we win? And that means we get to choose the best possible outcome for us. I don't know what the point of randomization was actually, but I guess that's the idea. So accidental victor, yeah. So basically, we can win if we don't have fewer coins than the other one. If we have at least as many coins as our opponent. All right. Now consider the current player. Now consider the smallest player that hasn't been beaten yet. Either it has too many coins. For example, say we're facing 2 against 3. Either it has too many coins, in which there's nothing we can do that. Because this has the least amount of coins, because we picked it so, every other player has at least as many coins, meaning we can't ever beat any other player. It's just too many. But if we can beat this player, then we get more coins and this player is eliminated. So we might as well beat this player and then continue moving on to later players. So really, the algorithm would be to check the current player with the least amount of coins. If we can't beat it, then we'll never beat any other player, so we're done. Otherwise, we might as well beat it and continue beating players. So that's the basic idea. However, this is O of n squared, which is not good. We need it to be faster. So let's make it faster. Notice that if I can win and I have a certain amount of coins, then if someone else has more coins, then they can beat me. Or if someone has at least that many coins, then they can beat me, meaning that they can have at least as many coins as I do, and they can beat someone who can win the tournament. Meaning that they now have more coins than someone who can win the tournament, and they're still, like, in the same position. So they can also win. So if we find someone who can win, then everyone with more coins can also win. Or everyone with at least as many coins can also win. And if we find someone who can't win, then someone with fewer coins obviously can't win because they can beat strictly fewer players. So really we have something like this, where we have a bunch of people who can't win up until a certain point. And then we have a certain point x, where every amount of coins after x can win and every amount of coins before x cannot win. That's interesting. That sounds a lot like binary search. Why don't we do that? So why don't we binary search on the answer x, where everyone with at least as many coins as x can win and everyone else loses. We can do this smoothly by simply sorting this array, or we can create a sorted version of the array while still maintaining the original array. And then we can simply do this binary search to check. We binary search on the value that we have, meaning that we have O of n possible things to check, and to check a value, or to check a specific index. Like, say we're solving for this. We already have 3 coins, and we can have it eat up all the players before it. Like, these are just free coins, because we already know we're better than them. So now we know we have 6 coins, and then we iterate... Sorry. We iterate through the remaining players in order. In ascending order, because again, if we can't beat the smallest, we can't beat anyone else. And then we see if we can beat the current player, which is the smallest player, and if we can, we gain their coins and move on, and if not, then we can't. And that's how this binary search would work. So then once we have the value x, for every player, we can just simply check if they have at least x coins. And if so, then we include them in the answer, and if not, then we don't. You can also sort an array of pairs of values and indices. So for example, this would be 1 in index 0. This would be 2 in index 1. This would be 4 in index 2. And this would be 3 in index 3. And that way, what you can do is, once you do the binary search, you can, you know the original index of every player that you know can win. So you can print those indices instead of their positions in the sorted array. Multiple ways to do it. So for f, we have an array. Say for example 1 3 2 1 4 2, and we're interested in the frequencies of these. So for example, like, let f of I be count of I in the array. Then we're interested in the frequencies of all of them. So f of 1 is equal to 1, f of 2, f sub 2 is equal to 2, or sorry, f sub 1 is also equal to 2. F sub 3 is equal to 3, no, 1. And f sub 4 is equal to 1. And basically, we want to pick some value c. And then we can remove some values from the array so that every frequency is either 0 or c. And we have to remove some elements. So say we want to pick c, or we want to find the optimal c so that it minimizes the number of elements we want to remove. But say we do know c in advance. Then what are we going to do with a certain element? Well, we have to either remove some of it or we don't. So if f of I is greater than or equal to c, then because c is greater than or equal to 0, it's always going to be better if we wanted to have c occurrences than having 0, because it means we're going to have like c fewer operations. We can keep c elements. So that's a good thing. Yeah. So then the answer for this element is simply fi minus c. This is the number of elements we need to remove to make fi to c. Otherwise, then the answer is fi. We have to remove all of them because we have to have 0. So now, how do we check a c? Also note that, like, we can sort of do this with like prefix sums or things like that. A lot of things will work. But how do we check so that's how we check a c. We can check a c in O of n. But what c is we actually interested in? Well, say we have a c that doesn't occur as a frequency in the array. Like, for example, say our frequencies are 1, 3, and 4, and we check c equals 2. But what if we make c equals 3 instead? The number of elements that are greater than or equal to c will not change because c wasn't originally an element in the frequency array, meaning that yeah, c wasn't an element originally in the frequency array, meaning that yeah, like, there's not going to be an element that's equal to 2. So therefore, if we increase it, the number of elements that are greater than or equal to it won't change. So that means that all we're going to do is increase c. And since every element that involves c will subtract it, increasing c will decrease the answer, which is what we want. So if there's a valid C that's not equal to an original frequency in the array, then we can increase it to an original frequency and have just as good an answer. Meaning that the only values of C we need to try are those that are original frequencies. And the final step is that because, like, say we want X distinct frequencies, the easiest way to do that require the least amount of elements would be like 1, 2, 3, 4, 5, 6, etc. up to X. Meaning that we have, in total, this requires X times X plus 1 over 2 elements. Meaning that in total, this is O of X squared, meaning that the maximum X we can get is O of square root N. So if we try only the frequencies that are originally in the array, and we can either do O of n or O of 1 checking with prefix sums either way, it means that we have O of n root n or O of n or something like that. There are a lot of ways to do it once we figure out that the frequency has to be an original frequency in the array. Either way, it should be relatively fine. So yeah, that will leave G. And the way this will work is, alright, this one's the most annoying. So we have a circular disk. So for example, let's take this. So 1, negative 3, and 4. And what we're going to do is we're gonna pick some value. We're gonna pick some target value X. And what we can do is we can move a pointer sort of around the disk, and every point we move to, we gain the value at the position in the disk. So for example, say I do this movement. Then this would give me plus 1, minus 3, and plus 4, so the total would be 2. Positive 2. Then because it's a circle, and then once we get to the end, I can move it back around and continue moving like this. And continue gaining the value. So this motion would give us 4. If I excluded this last motion, then we would have 1 plus 3, 1 minus 3 plus 4, 2, plus 1 minus 3, which is in total 0. So for our target value X, what we want to do is we're going to simulate doing this motion where we start here and then go to the next position and then go to the next position and then potentially circle back around and then go back here and then go to the next position and etc. And we're interested in the first point where our current sum is at least X. So when do we have at least X elements? Yeah. So for example, say X equals 5, which is one of the queries. So what we would do is first we would go here, we would have 1, then we would go here, we'd have negative 2. And it's like we're interested in the minimum amount of movements, meaning that the first element doesn't count as a movement. And then here we have 2, then we continue, we have 3, we have 0, we have 4, and then finally we have 5. So the number of movements this took was 6, because we did these, and then that, and then that, and then that. So it took us 6 movements in total. So something we can do is, first, how do we solve this? We also have a lot of queries, so we can't like simulate it. Definitely not, because it could also take infinite time. And in fact, we want to print negative 1 if it could possibly take infinite time to do so. So first, let's store the values we get at each position. We can do this by just simulating it. So now, when we go through this array, like say we have a negative 3 here too. Then basically what this does is this value is going to be the maximum we get in this rotation. Well, the first thing we want to do is figure out how many times we have to go through the circle first. And then we can sort of, once we know that we've gone through the circle like y times, and then we have a sum of, like we have a certain sum a, then we just need to figure out at which point on the circle is a plus the prefix sum of the elements going to be greater than or equal to x. And we can do that by binary searching, where we store at every point the maximum prefix sum that's been encountered so far. So for example, this would be 1, then this would be the maximum of these two, which would also be 1. This would be the maximum of 2 and 1, and this would be the maximum of 2 and negative 1. And that way we get a strictly we get a non-decreasing array. It's a sorted array. And then we can binary search on this and find the first point where this value is greater than or equal to x. And then that would give us the answer. And our answer would be n times y, where we make y rotations, plus the index that we get. This would be 0 index because, again, the first element, the first rotation, the first movement, or like starting at the beginning doesn't count as a movement. So if we know y, we can do binary search, and that works. Now the only question is, how do we figure, and that works in O of log n per query. The only problem is, how do we find y? Let's do some casework. Let S be the sum of all elements in the array. Now, okay, say we know that y is not 0, and therefore the biggest prefix sum that we ever get is less than x. So let like m be the largest prefix sum we ever get. Because we know m has to be relevant. Like the largest prefix sum we get would be this. This has to be relevant in determining the number of rotations, because we're interested in a particular rotation, do we ever get good enough? And checking the best we ever get will help us find out if we ever get good enough. So we have some cases. If s is greater than or equal to 0, then doing a rotation won't help us. In fact, it may even make the answer worse. So if s is less than or equal to 0, we have to do it in our first rotation, because making more rotations isn't going to make it easier. We want to increase the value we currently have. So we have to do it on the first rotation. So we have to make 0 complete rotations through the array. So this is simple now, because we only have to check one rotation. So really, we just check if m is less than x, then no matter where we go, our best ever value is not going to exceed x, or is not going to be at least x, meaning that we'll never be good enough. So the answer is negative 1. Otherwise, if m is greater than or equal to x, then we will get it in this rotation. So we know that y equals 0, and we can do the binary search as planned. Otherwise, we know that s is greater than 0, meaning that even if we're small enough, eventually we should be able to make some rotations to get it, because every time we do a rotation, we increase our total sum. So if s is greater than 0, it's always going to be possible. And in fact, the number of rotations we have is, say m is greater than or equal to x. Then we know that y equals 0, and we can do binary search. Otherwise, so that's it. Otherwise, m is less than x, meaning that y is greater than 0. How many times do we have to do a rotation before we're good? So we have a target x. We have a current sum 0. We get s per rotation. And we know that we're going to get it on the rotation where m plus the amount of rotations we do times y. Like, we're going to get it where m plus the sum we've accumulated by doing rotations is greater than or equal to x. So the condition we have is m times, or no. So the amount we get from doing the rotations is s times y, the number of rotations we do. And then we're also interested in the maximum prefix sum, so add m to that, because we want to get it in this rotation. We want to get it after y rotations, and we're checking if that's possible. So if s times y plus m is greater than or equal to x, we're done. So let's solve for y now. We simply subtract m from both sides, x minus m, and then voila, we do some division. So we're interested in the smallest integer y such that y is greater than this division. And this gets to the point of being the definition of the ceiling function. The smallest integer y such that s times y, in fact, this is the definition, I think. The smallest definition y such that this division works out. So y is equal to the ceiling of x times m over s. So that's how we find y. We just take this value. And then we can also binary search on y or do whatever. It doesn't really matter because we have log complexity anyway. But then the answer is going to be this formula we derived earlier, n times the number of rotations we do, because each rotation uses n moves, plus binary search. So that's how we would do it. We do this sort of k-circ and we figure out how things work. And in fact, perhaps it's easier to make this a uniform case, and then we only have 3 possible things to do. But either way, it doesn't really matter how you do it. You just have to figure out that if the sum is negative, then it may never be possible, and otherwise, or if the sum is non-positive, then it may never be possible, and otherwise, then we have to figure out how it works. Okay, so yeah, winning a round. How cool is that? That's all I got. So you better believe this is going to be in the title. Yeah. Awesome. All right. Hope you understood everything. And yeah, this was really good. See ya.